Okay. Are there any questions before we? Okay, so we're going to continue talking about vector spaces. The idea is to discuss some vector spaces you can associate to a matrix. Okay, so uh, I may keep this throughout the lecture. So the idea is that if you have a matrix A, well, there are actually four things you could associate with. The first one is null space. So the null space is the one that I wrote last time. Okay, that just consists of the vectors that solve like a homogeneous system. So the null space is the vectors V that solve AX equals 0. Okay, so it is basically you look at all the solutions to this homogeneous system. The idea that we showed last time was that that actually does form a vector space. And there's like a big theorem in linear algebra called the rank nullity theorem that tells you that the dimension of this null space is the nullity of the matrix. Okay, so the dimension of the null space is the nullity of A, which again, remember that it was just the number of columns of A minus the rank of A. So that's the first vector space that you can consider, and I'll give you in a couple of minutes some other examples where we compute this null space. Okay. The other vector space that you can build out of a matrix. So maybe to make this more concrete, let me write a matrix. Uh, yeah, let's keep a specific matrix in mind. Just to think about this. So imagine that I had given you like a matrix A, which is 1, 2, 0, -4, 0. Um, 0, 0, 1, 3, 0, 0, 0, 0. Okay, so if you look at a matrix like this, so this is a 3 by 5, right? So this is a 3 by 5 matrix. And another, in addition to looking at the homogeneous system, another thing you could look at is like, well, remember that a matrix is like a collection of vectors. You can think of the vectors that make up the matrix as being its columns. You can also think of it as being the rows. So for example, if you look at the rows of this matrix, right? It has three rows, which are three vectors. So row one, let's call them row one, row two, row three. So it's two. Okay. So there's another space that you can build, which is called the row space, which is essentially all the vectors that you can create or obtain by taking linear combinations of these vectors, of the row vectors. So this is called row A. Let me put it here. All the vectors B, which can be written as linear combinations of the rows of A. Okay. So just to give you an example, let's say I had given you the vector, which one is okay, yeah, let's do this too. So imagine I had given you the vector two, one. So here's that example. So the question would be whether or not this belongs. Does this belong to row A? So what I'm asking here is, I mean, first of all, this vector is not, I mean, it's different from any of the rows of the matrix, right? But what I'm asking is whether I can produce or express this vector in terms of the rows of the matrix as some sort of like sum, right? So is there like a way, looking at the rows of the matrix, what do you say? Is that a possibility? Yes or no? I mean, I'm trying to do it kind of by eye, like, it should be either relatively easy to check for this example whether or not it works. So. Right. In this case, I made it so that it would be just row one plus row two, right? So yes, since it is row one plus row two, right? And something like row one plus row two plus three times row three would be in the row space. Like, you just imagine like putting whatever coefficients you want in front of the rows and taking their sums. And that's how you start generating or creating the row space. That making sense? How about the following? So how about this one? If I look at the vector 1, 1, 0, 0, 0, does this vector belong to the row space? Why not?
Because once you like start manipulating, you can see that there's no way to get like the second one or the first one or the second one vector, because you can like take the first one, you can make it half, but then the first one becomes half, and you can't do anything to make it go back to one.
Yeah. So the thing, I mean, what's happening here is like if you look at, I mean, if you look at the last two rows, right? The last two rows start with zeros here, right? 0, 0, 0, 0. So when you take linear combination of the last two rows, like, you know, the first two entries would always be 0, 0, or like, you know, coming from any linear combination from here. So the only way that you would get like a 1, 1 on the first two entries is thanks to the first row, right? But for, what would you need from the first row? I mean, since the first, like the ones agree, right? Like it seems like the scalar multiple should be 1, but since that this one is 2 times this one, like you would have to rescale it by a half to make it coincide. So it cannot be simultaneously of the same size and have the size, like if you know what I mean. Like if you want to, so it is no, if you want something more precise, like, you know, you just check that you cannot solve right, there's no way to, you know, combine the three vectors in such a way that you would get, like, you know, this vector. Like there was like a system of equations that you can create here, and that system of equations would have no solutions. But like, you know, I'm trying to give you some examples pictorial, kind of like that by eye, you would see what's this is like. But it's just to give you like a sense of like sort of what the row space is supposed to be like. It's just, you take the rows, there are vectors, just think about all the vectors you can produce out of the rows of the matrix. I mean, this would be useful later, like towards the end of the course when we talk about like some applications like least square methods or things like that. Because like you can rewrite those like, you know, for least squares methods or things of that sort, you're trying to, like, you know, create like a curve that fits certain data. And so it is important to know in that case, like, you know, you don't expect like a perfect agreement between the theoretical values and the experimental values, for lack of a better word. And so it is important to have like some understanding of when you would expect, you know, certain things to be within the range of the theoretical, like, you know, certain data or things like that. And for that, you're secretly asking whether something is a linear combination of other things. But I mean, this will be made more precise once we get to that point. But it will be used eventually for like things like least squares method or other things. Okay. So this, I mean, this is just to give you an idea. Let's say I had just to. This is a very silly matrix, but it's actually going to be very useful for many things for today. So imagine I had given you that matrix, right? Very simple, which is 3 by 2. Right, so now these are like the first row, the second row, the third row, right? What can you notice? What's a somewhat clear relation, hopefully, between the rows of this matrix? Like, how are they set up?
The rows are linearly dependent.
Well, yeah, it's even more than that. It's just literally in this case, they're like, you know, this one is twice as the first, right? Like the second row is twice the first row, and the third row is 3 times the first row. Meaning, like they're just like if you thought of them as actual vectors, one is a rescaled version of the others, right? So they're like literally pointing in the same direction, right? Like if you have to do like a picture like of the rows, like here's like row 1, right? 1, 1 is kind of like 45 degrees, right? Row 2. And somewhere in here is row 3, right? That making sense? So I mean, one way to think about it is that like the information that these rows carry is redundant, right? Because just knowing one row has all the information as like, as like what you're getting from the other two rows, because like these other two rows are just essentially rescaled versions of the first one, right? So what I'm trying to say here is that the row space of this matrix, right? Row of A should be the same as the row space that you get from, like let's think of this mini matrix where I just keep the the first row, which this is now what, like 1 times 2 matrix, right? Like I forget about the other two rows because they're kind of redundant information. So what I'm trying to say is that the row space of this matrix should be the same as the row space of this smaller matrix. Is that making sense? Because like the first row is really the row that carries all the data. So the reason why I mentioned this is that what I'm trying to say is that sometimes the rows of the matrix are redundant, right? Like they carry redundant information. So if you want to find like a basis for the row space, right, there's some simplifications that need to be done. Because again, like the point of this course, more or less, is always to find a basis for a given vector space. Like finding the basis is like the most important goal all the time. So it's not that you just like, the basis is not going to be just like the rows of the matrix, because sometimes there's like overlap between the rows. So you have to be a little bit more clever about what to do. Does that make sense? So just to give you, now that I mentioned these two examples, let me tell you two other things that you need to know about the row space. So this is going to be a vector space, as I was saying. So it is a vector space. And the important thing is like the dimension of this space is the rank of the matrix. Okay, that's another important theorem. The dimension of the row space equals the rank of the matrix. Okay. So that's another reason why the rank was an important quantity to compute at the beginning of the course. And in fact, to find a basis for the row space, you just reduce a matrix using, elementary row operations until you get to the row reduced echelon form, and the vectors that you get there are a basis for the row space. So let me write that down. So to find a basis for row of A, you basis for row of A, reduce the matrix A until getting to the row reduced echelon form. And the non-zero rows are a basis for the row space. And the non-zero rows will be a basis. I'm about to do it in those two cases. Let me continue. Okay. I mean, I'll probably keep writing this on the other, use other kind of this form. I won't try to write it. So. So just to go back to these two examples, if you have the matrix A, let's start with the simple one because we have more intuition about what this looks like. If you start reducing this matrix, right, using the row operations, like, well, you can just do minus row one plus minus 2 row one plus row two into row two, right? And then minus 3 row one plus row three into row three. And you get 1, 1, 0, 0, 0, 0. Okay. In this case, there's no need to augment the matrix with anything because we're just looking at the matrix itself. And this like is the most you can reduce it, right? So what I'm saying here is that you look at the non-zero rows, right? There's only one non-zero row, which is the first one. And so the basis for this matrix, right, for the basis for row of A is the vector and notice that the rank of this matrix is 1, so the basis only had to have one vector, right? So the dimension of the row space is 1. Sorry, is the rank of A, which in this case was 1. So that means that we only were supposed to find like a single basis vector. Okay. That making sense? Like a lot of like this stuff is just reducing matrices, like literally, you know, it's just that now we're reducing matrices and we're giving some extra interpretation to what we're doing. Before it was just, oh, let's just reduce the matrix. Now it's like, well, this reduced matrix represents, you know, you find like a basis for some vector space or things like that. But the main tool that you have to know how to use is how to reduce a matrix. There's like 80% of the problem, like, you know, 75% of the problems we just involve like reducing a matrix to some extent on the exam. There's nothing else in terms of tools that we have available. That makes sense. How about the other one? For the other matrix I had written, which was this one. This one is on PDF. Okay, I feel that I made a typo in my notes, so let me get it right. Yeah, because this is already. So yeah, I don't know what I wrote here. Oops. Okay, let's do. Okay, let me take a different one because I don't know what's wrong with the one I put in the PDF. Like. This is like the one that we had used last time, this matrix. So this is a matrix from last time. Okay. And again, to reduce it, this one is so we can redo it here. You got 1, 0, 1, 0, 1, 1. And you can also do 3. And then from here, it's easy to see that this is, if you do minus row 2 plus row 3 into row 3, you get 1, 0, 1, 0, 1, 1. Okay. Yeah, so that's like the one we had found last time. Yeah, so I'll have to fix the stuff on the PDF. And actually, this is a better example. So here there are two non-zero rows. The rank is 2, right? And this is a good one just because you see, like, there was some redundancy between the rows, which was maybe not so obvious from the starting point, right? But like, kind of like information on the third row was already contained in the first 2 rows, right? That's what the row reduction method tells you. So the basis for the row space in this case is 1, 0, 1, and 0, 1, 1. We can call this V1, and this one V2. Okay, so it's 2-dimensional because we needed 2 vectors for the basis. So in this case, the dimension of the row space, again, it has to be the rank which is 2. And so that agrees again with the fact that we needed 2 vectors that we had 2 non-zero rows at the end of the reduction. That making sense? Any questions to this point? So it's not too bad. It's just reducing the matrices appropriately. So again, we have the null space, the row space, right? There's a third one you can come up with, which is called the column space. Unsurprisingly, because we're trying to make vectors out of a matrix. So one way to get vectors is to look at the rows, but another way to get vectors is to look at the columns. So when you have a matrix A, you can also look at the column space. Let me write it next to the row space. Or yeah. And what is this going to be? Well, it's just going to be all the vectors that can be written as linear combinations of the columns, right? So it's not too bad. All the vectors. So for example, if A, hopefully this one is good. So it's 1, 1, 2, 0, 2, 0, 2, -2, -1, 1, 0, 2, 0, 1, 1, -2, 1, -1, 0, 2. So this is what? 4 by 5 matrix. So you have column 1, column 2, column 3, column 4, column 5. So how about, again, hopefully this is recognizable just by looking at it. How about this vector? Would this one be in the column space? Which one do you think of? Yeah.
You do like 2 times or column 3 plus 2 times column, or no, just you do column 3 plus column 5.
You could do column 3 plus column 5. Yes. Would there be another way to do this one? I mean, there could be other ways. I mean, it may not be, it's useful to see that it's not necessarily a unique way to do this, and there could be other decompositions that work, but let me see if I can come up with one that. Yeah, I mean, like, I'm trying to, should have thought about one that would have worked like in different decompositions, I think. Just because we found that it is column 3 plus column 5. I mean, there could be other ways to break it down in terms of the columns. That's what I'm trying to say. Sometimes, like, in fact, if the columns are linearly dependent, that will happen. Like, there will be multiple ways to break it down. It's just that by, just like that, I can see easily by eye, like this is the most obvious one. But yeah, there could be like, there will be other combinations that in general would do the trick. I mean, this is a, let's see. So, a pattern. But yeah, the important thing is that it is in the rows in the column space. But, and then you say, well, if I gave you a vector, I mean, but it is more, it would be harder to, check this, whether something belongs in the column space or not, because there's so, I mean, there are like 5 columns. So, you want something a little bit more systematic. It's not, I chose like something where it was just easy to identify it, but in general, like you would have to set up, if I gave you like a concrete vector, maybe you wouldn't be sure, and then you would need to say, well, can I find like the coefficients, right? That would do the trick, but that can be like somewhat tedious process. Okay, but just to keep continuing with these other examples of like the matrix from before, which is 1, 1, 2, 2, 3, 3. In this case, it would be the first column, the second column. Right now, this is like a 3 by 2 matrix. Right. And if you compare the columns, I mean, basically they're identical, right? Like the second column is the first as the first one. So in this case, you would like to say that the column space of this matrix, right, should be the same or is the same as the column space of the matrix B, where B is just like the matrix that gives like the first column, right? Is that making sense? And essentially, you know, one way to think, yeah. Oh, this B, you mean? I mean, it would be either of the either of the two columns, right? Because they're the same, but oh, sorry, or was these two matrices are completely separate from one another, but yeah, what is that making sense? So I'm just saying, like the first, like, you know, these two columns are identical, right? So the information from the two columns is being repeated. So all the information about the column space should just be obtained from one of the two, right? So that's what, which is one of these columns I'm just calling the matrix P. So that's why I'm saying that the column spaces should be fine. Is that okay? So now, you know, one way to think about getting to that is like you would say, well, maybe we would like to do like something like minus column 1 plus column 2, plus column 2, right? Like kind of canceling columns, like in the same way in which we have done it for rows. And we will, it's just that we really study the operations in terms of rows, not of columns. So but we know there's a trick to turn rows into columns, right? Which is by looking at the transpose. So what we can do is like taking the transpose of this matrix, right? You take A transpose, which would just like, you know, switches rows into columns. When you take the transpose, it just looks 1, 2, 3, 1, 2, 3, right? And then like here, we just restate this in terms of the row operation. So you would say, well, let's do minus row 1 plus row 2 into row 2. And you would get like 1, 2, 3, 0, 0, 0. And so you see like the vector itself, it just is the same that we would get before. So what I'm trying to say, is that making sense? So it's just like, instead of like doing directly like the column operations, because that's not kind of how we learn this stuff, we would just like do like row operations, but on what? On the transpose. So essentially the thing that happens is that the column space of A is basically the same as the row space of the transpose of A transpose. Like that's the important thing to know. So actually like finding, you know, the column spaces is the same as finding row spaces, but you're just working with the transpose matrix. Okay. Does that make sense? Yeah.
Does that mean that like you have a square matrix dimension column?
Oh, it's even better than that. Well, it wouldn't. I mean, you would have needed like a symmetric matrix to say that for sure, right? But no, it's even better than that. There's like also. Let's see. Well, before answering that question, so like, is that making sense? Like, why you would just like transpose it to the same? The dimension of this, right? So let's try to, let me put this in a different color to emphasize it. So what should the dimension of the column space be? Well, it should be the dimension of the row space of A transpose, right? But what is the dimension of a row space? It is the rank, right? So it should be the rank of A transpose, right? So this should be the rank of A transpose. But then one of the most important theorems of linear algebra says that the rank of the transpose is the same as the rank of A, which is highly non-obvious. So there's like a very important theorem. Let me write it. But yeah, it's like one of the main results of linear algebra that, but one can prove that, I mean, it's on the PDF, but like, again, like the proof kind of painful to do it in class. So it's not, I mean, someone can read it if you're really interested in seeing it. It's not too bad, but it does require some manipulation with like multiplication of matrices. So it's not ideal to do it in class, I think, but one can prove that the rank of A transpose is the rank of A, and that holds in general, so. So what you end up with is basically saying that the dimension of the column space continues to be the rank of the matrix A. There's no, it's still the rank. So. This is what I was trying to get at. Okay, this is like, again, one of these fundamental theorems of linear algebra kind of thing, like the ranks. It doesn't matter what, I mean, it's kind of surprising because, again, even if this is also true, even if the matrix is not square, right? Maybe it would be more believable, you know, in general, if you didn't know anything, like that this would be true for square matrices, but it's even like the case in the non-square case. Well, here, like you can see it very clearly for this special case where like the rank is 1 for like the transpose, and it was also 1 for the original matrix A. But it's just saying that this holds in general. That making sense? Like the vectors and like the basis or the vector spaces can be very different, right? Because for example, the row space here has like the vectors have 3 entries, and the column space here, like the vectors have 3 entries, but in the row space here, the vectors have 2 entries. So the vector spaces themselves can be very different, but the number of elements in the basis is still the same, 1 and 1 in this particular case. Okay. Any questions about this? So again, it is just conceptual. I mean, it's sometimes a little bit of information to process, but in terms of like skills, like the only skill we're using is like reducing the matrix, right? You just have to remember now which matrix you're reducing. Like, so when you're talking about the row space, you just reduce the matrix A, and when you're talking about the column space, you reduce the matrix A transpose, right? So that's basically the main difference here. So let me do it let me do it for this example, which was a little bit more tricky because so what is in this case for this A, what is the column space of A? So again, what you have to do is use this fact that the column space is the row space of the transpose, right? So column space of A is the row space of A transpose. But what is A transpose in this case? Well, remember, like the transpose turns rows into columns. So like it would become 1, 2, -1, 0, 1, 1, 0, 1, 1, -1, 2, 2, 0, 1, 0, and then 0, -2, 2, -2, 2. Let me check because transposing this matrix can be a little bit tricky. And so far so good. So yeah, then what I did was put this sample from alpha to have it reduce the matrix for me, because I mean, obviously in practice I wouldn't give you a matrix that is I wouldn't, I mean, it does take some time to reduce it, but you know, like I'll give you more friendly matrices for reducing it, but I just wanted to illustrate it. So yeah, I went to Wolfram alpha, and this reduces. Try to check that this reduces to using row operations. to this matrix, like 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, and 0, 0, 0, 0. That makes sense. So we got the rank is 3, right? Like the rank of this matrix is 3. So the rank equals 3. So that means that the dimension of the column space will be 3. Right, and the basis would be these 3 non-zero vectors, right? It's just that because we were talking about them as column vectors, because we're looking for a column space, it's kind of more appropriate to rewrite them as column vectors, like kind of undo the transposing. So it is like there's the same vectors, but it does look a little bit better. So the basis is 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1. Is that making sense? So this is V1, V2, and the 22. And just, I don't know if you remember our old friend, the 0004, it's just 4 times now this last vector, right? So it's a lot more clean, more clear that this vector was in the column space, right? Because like here you just see it as 4 times the multiple of this one. And you don't have to think about it, which columns do I have to add or things like that. It is more like straightforward once you have the basis to like check whether a vector is or not on the column space. Because like the vectors like in the basis are kind of like, the idea of finding a basis is that you find vectors that do not overlap in terms of information in some way. So like these 5 vectors, like the 5 original columns kind of like overshared, they were not completely independent of one another, right? Like there was some overlap of data. And this is kind of like the clean version of the vectors, right? They still contain the same data, but it is less. Like, if you wanted to, you could, like this big data thing, it is like kind of, how would you store this matrix? Well, how would you store like the information here? Like you would need like, imagine that you needed like, it's like 4 times 5, so you would need 20 numbers, right? To store this matrix. But if you only get like, or to store like something that's giving you the column space, but here, you need 4 times 3, so it's 12, right? So here you would only need 12 numbers to store the information about the column space, which doesn't seem like much of a difference, 20 versus 12. But then if you're thinking about something that like big data where you analyze like millions of like records or like pictures, or, like the vectors, like in a picture, like when it's broken into pixels or things like that, you can describe them in terms of vectors. And then it would be like the difference between like, 20 million numbers versus like 100,000, or whatever, just to give some numbers. But I'm just saying like, it can become like a big difference, like, once you're dealing with huge collections of data to whether you are storing things in terms of a basis versus like just storing things in terms of the original vectors of the matrix. Okay, let me see where I should. Okay, so, well, maybe just keep working here. So you had a matrix, you could find its null space, its row space, its column space, which ends up being just the row space of the transpose, right? So I'm claiming now that there's only one more like space that's missing here, and then I'll tell you how you can think about it. So there's a last one that we could write. Anyone wants to give it a shot? What could be the that one? This one was a row of A, right? And this one was a row of A transpose. What were you going to say?
I was gonna say maybe a combination of both the row and the columns.
Well, it is more like, well, here we're using the row space of A and we're using the row space of the transpose. So the transpose is appearing once on this diagram, right? But yeah.
The row space of the inverse.
Well, it may not be necessarily invertible because the matrices may not even be square. It's more like, you know, let me say in a different way. How many times is the matrix A appearing in this diagram? Well, once here, another time here, so 2 times. How many times has the transpose appeared on this diagram? Just one on the row. So to make this entirely symmetric, you should have like the transpose appear somewhere else here. And so like what's, I mean, maybe it's not so clear, but what's left is the null space of the transpose. Okay, so just to make this super like symmetric, because now you have the null space for A and it's like, you know, now you have like null space for A, the null space for the transpose, and then you have the row space for A and the row space for the transpose. So it's like 2 and 2, and that looks a lot better. That's what I'm trying to say. And actually, you'll see that it is not a bad thing to look at for what I'm about to show you. So the null space for A transpose, I mean, it's just like what solves, this one solves A transpose X equals 0. And what's the dimension of the null space of the transpose? Well, it's the same formula, but just for the nullity of the transpose, right? So what's the nullity of the transpose? Oh, is the number of columns of A transpose, right? Minus the rank of A transpose, right? That would be the formula. That making sense? But you can rewrite this if you want in terms of A itself, because what's the number of columns of A transpose? That's the number of rows of A, right? So this is the number of rows of A minus the rank of A transpose. But remember, I told you the rank of A transpose is the same as the rank of A. That making sense? So, I mean, I'll basically have ready like the midterm study guide for the second exam. So I made like a kind of roughly like a table with all of these 4 subspaces. But these are like the 4 subspaces that you have to think about it for a matrix. Okay, 2 are row spaces, right? Row of A transpose, and 2 are like null spaces. Null of A and null of A transpose. You have to remember, like, you know, like dimension formulas and those things. Okay. So let's try to see how the 4 of them look in a super simple example, because then we can visualize everything. So So let's try to look at these four spaces on a picture. So let's do it for the matrix that it was 1, 1, 2, 2, 3, 3. Okay. So let's start with the row spaces. Right, we had found before like a basis for the row space of A, right? What was the basis vector for the row space? It was just 1, 1, right? So what's the vector? So if you want like a picture, the vector 1, 1 is here, right? And the row space is anything that's like a linear combination of this vector. So it's, since there's only one vector, it just means it's any multiple of that vector. So it's like a line going through the origin in the direction determined by the vector. So let me put it this way. So the row space is just this line. Is that okay? Because the row space, again, like the dimension of the row space is 1 because there's only one vector in the basis. So it has to be something one-dimensional, and something one-dimensional is actually like a line. Okay. And then what was the column space, right? What was a basis for the column space? It was the first column, right? Like 1, 2, 3. So if you want a picture, I cannot draw it on the same picture, right? I need to go to 3 dimensions. So here, this is on R2. Here's on R3. I mean, this one is a little bit trickier to draw. It doesn't matter whether, I mean, for drawing this, it's not so important whether you're putting it, you know, in terms of a row or a column. It is that it would still represent the same vector visually. So the columns, this is the column space, and this is the basis vector, and the column space itself is again like the line going through this vector. So this is the column. Is that making sense? So, but we still have 2 more left to draw. Let me see if I can find it. So we have the null of A, right? What is null of A? We haven't computed this one. Let's see. So if you remember null of A, what that means is that you have to solve the homogeneous system. So for the matrix A, so you do 1, 1, 2, 2, 3, 3, and you augment it with the zero vector, right? When you reduce this, you get to 1, 1, 0, 0, 0, 0, 0, 0, 0, right? This one is not too difficult to reduce. And so in the null space, like the difference between the null space and what we were doing in the row space is that now in the null space situation, you have to reinterpret this as a system of equations. So when you think of this as a system of equations, this is telling you that x plus y equals 0, right? So that means that y equals negative x. Is that making sense? So a vector in the null space would be x comma y, but x is just x and y is minus x. So this is just x times 1 negative 1. Is that okay? So what I'm trying to say is that a basis is just a basis for this null space is just it's one negative one. That makes sense. So that's how those two vector spaces look on the left-hand side, right? One is this line and the other is this line. Okay. Now, is there anything, maybe if the picture is kind of done properly, is there anything that you can say about those two lines, how they look like in the picture? Yeah. Yeah, they look perpendicular. I mean, that should be believable because, you know, the angle between this and the x-axis is 45 degrees, you know, because it's 1, 1, so it's like an isosceles triangle. And this is also 45 degrees, right, because it's 1, 1. So 45 plus 45 is 90. So they are perpendicular lines. And like what will happen, but this will take a little bit towards the end of the course because we have to talk a little bit more about when two vector spaces are perpendicular, which will take some time. What will happen in general is that the row space is always perpendicular to the null space. So it's not like a specific, it's not specific to this situation, is that whenever you draw them, they always come up perpendicular or orthogonal. But it's just like in this picture, it's not, in this example, it's not because you can actually draw them very nicely and see that it all works out. Okay. I'll show them. And then there's only one more left, right? Which was what? The null space of the transpose. That's the only one I haven't computed for you. So what's the null space of the transpose? But for that, you have to transpose the matrix and look at the homogeneous system. That's how you find a null space in general. So this gives you 1, 2, 3, 0, 0, 0, 0, 0, right? So again, like it is a homogeneous system. So you look at this as x plus 2y plus 3z equals 0. And from this, like the best you can do is just solve for one of the variables. So you can say that x is like, for example, minus 2y minus 3z. Okay. Let me see where I can continue. So like a point xyz in this case would be like minus 2y minus 3z comma yz. And I don't know if you remember this. What you do is like split the stuff with y, split this, keep the stuff with y together in a single vector and the stuff with z in a separate vector. So this gives you minus 2y comma 0 plus what? Minus 3z 0 z. Okay. And from there you can see the basis, right? Let me finish it here because you can factorize. Sorry, you can pull out like the y, so you get y times minus 2, 1, 0 plus z minus 3, 0, 1. So the basis, right? Like the basis. So the basis for this one is negative 2, 1, 0, negative 3, 0, 1. That making sense? And that one may be a little bit harder to visualize. So let's try to see how this is supposed to look like. Don't you have to run? but I won't use it. Okay. So we have P, which is 1, 2, 3, and then we have the vector which is P. Okay, that was the first vector I drew for you. The one that was the row space and the transpose. Okay. That was in green on the board, so let's change the color here. And then we had two other vectors which I wrote. I have them here, so. Which was Q negative 2, 1, 0. And let me draw the vector U, which is Q. Okay. And then you had the vector R, which was negative 3, 0, 1. And let me call it W. Okay, so I think this can be getting a little bit confusing. So now we look at these vectors. So like these other, the black ones are the ones for the null space of the transpose. What can you tell me about these vectors? Is there like any obvious relation between the green one with the black ones? How do they look? Yeah.
Vector space of null A where it's imperpendicular, because they form like a playlist.
It looks, well, I mean, hopefully it kind of looks like there's some 90-degree angle between the black one with the green ones. And yeah, indeed, there is a plane. What's the equation of the plane? Let me see if I can, I don't want to. Let me just write this for a second. What's the equation of the plane going to be? Like the equation that gave you the condition for the null space. So if I go to GeoGebra again, like let me go back to GeoGebra. So if I go to GeoGebra, so if you go to GeoGebra and write x plus 2y plus 3z equals 0, you see that the two vectors are contained in the plane, right? Let's see if I can change the color here. Right, what do you see here? Like you see the two vectors are contained in the plane, and the green one is a perpendicular vector to the plane. Okay, so what would happen is that the null space of A transpose is perpendicular to the row space of A transpose. Okay, so what I'm trying to say is that of the four vectors that we got, like you kind of like put them in pairs, you know, 2 and 2, and like those pairs are mutually perpendicular to one another. This is, again, something that we won't use like right now. I mean, we'll mention it later on the course once we talk about subspaces being perpendicular to one another. But it does give you a better idea of like, you know, how they sit geometrically in space, because they're kind of decomposing the space into mutually perpendicular subspaces, like, which again, like for now, it doesn't, it's just a little bit of words and you don't have to worry too much about, but like the idea is that there's some sort of like 90 orthogonality or perpendicularity going on. Okay, so let me, just to finish today, let me just put this, put it on. So what I'm trying to say is that if you were to draw this, this should have been perpendicular. And these are also perpendicular. And the idea is like this doesn't happen just for these vectors, but will always be the case in general. So in general, the null space of A is always perpendicular to the row space of A, and the column space of A perpendicular to the null space of A transpose. Okay. And again, so this perpendicularity stuff, we won't use it right now, but that's more or less, yeah, kind of nice to know, at least for now. Okay, so that's more basically everything that I had to tell you about subspaces for now. And this is more or less where I'll stop the material for the second midterm, because there's just a lot of things that I can already ask from this. Like the second midterm is like in 26 days from now, so there's still a lot of time. It's just that, like we have the spring break, so that it's really effectively like 2 weeks. So what I'll do is like so one of the classes before the midterm, I'll do like a review session like last time. But we'll start after the spring break, with new material, which will be for the final, and we'll start with eigenvectors, which is also one of the most important topics of linear algebra. So we'll start with that, but it will be on the final. I won't put it on the second midterm. So officially today is where this material stuff for the second midterm ends. So I'll send you like a study guide for the second midterm either today or tomorrow. And yeah, we'll enjoy your break. I'll give you posted.
There be a new assignment.
Yeah, I'll also post like an assignment for you to work on during the spring break, if you want to.